Welcome back, guys, to our final part in a matrices where we will see how we can use matrices on solving linear equations by introducing something called Euclid form. So in this section, we will show how matrices arise when solving some systems of linear equations, and some of key concepts will be introduced, which are system of linear equations, argumented matrix, coefficient matrix, elementary transformation, Euclid form, rank of a matrix. So assume we do have the following system of equations, which are three equations with three variables. So from here, we cannot identify the values of x and y and z to satisfy the equations. Therefore, we just can transform this system to a new system to produce the solutions. And the new system is in Euclid form, where we just eliminate from down to up variables, so we can get the value of 1, substitute in the second row, get the value of 2, and then substitute the two variables in the first row to get the value of the third one. Now suppose we are going to transform the system of equations into a system in Euclid form, then we will reduce the labor, so we simplify the representation. Yeah? So from the system in here, we can get the argumented matrix. And argumented matrix consists of two parts. The first part is whatever in here. Then we have something like space, or you can put a line. Then we have the constant. So what are those numbers? They are the coefficients of the variable in here. You see? So we just write the coefficient of those variables along with the constant in here. Now our idea is to convert this representation or this argumented matrix to an Euclid form, where we here eliminate x and y, and then we eliminate x, and then we can substitute the values. All right, so how we can do this? Either by swapping equations, or multiplying through by non-zero, or adding one equations to another. So in terms of the argumented matrix, this means we might interchange two rows, multiply through by a non-zero number, or add one row to another. Or we can just combine the last two transformations, which are multiply by a non-zero and add. And we use those notations to show what we are doing in our matrices. Now the system of linear equation that we have, we converted from a system of linear equation, is what we have in here. So keep in your mind, we want to create an Euclid form where we have here zeros and the rest is in numbers. Yeah. All right. So first thing we will do here is we will make a change in row 2 by first multiply first row by 2, then substituted from row 2. So we can write row 2 in here, 2, 3, 2, and 7,000. Then we just multiply the first row by 2, so we will get 2, 4, 6, 12,000. All right. Then we subtract. So 2 minus 2 equals 0. Or we can write it here. 2 minus 2 equals 0. 3 minus 4 is minus 1, 2 minus 6 is minus 4, and 7 thousandths minus 12 is minus 5 thousandths. And we write this in row 2. Then the second change will be applied in row 3, where we take row 3 as 1, 1, 2, 4 thousandths. Then we just subtract row 3 from row 1. So 1, 2, 3, and 6,000. So 1 minus 1 is in here. 1 minus 1 is 0. 1 minus 2 is minus 1. 2 minus 3 is minus 1. And 4,000 minus 6,000 is minus 12. Then our next mission is eliminate minus 1 and put it 0. So to do so, first we can just multiply row 2 by minus 1. So we can change the sign in here. Then we add row 2 to row 3. So row 2 was 0 minus 1 minus 4 minus 5,000. Here we just multiply by minus 1. So we get 1 for 5,000. Then we add row 3 to row 2. So minus 1 plus 1 is 0. Minus 1 plus 4 is 3. And minus 2,000 plus 5,000 is 3,000. So here we just transform the augmented matrix to echelon form, and here we can just rewrite it in a system of equations. So we got x plus 2y plus 3z equals 6,000, y plus 4z equals 5,000, and 3z plus equals 3,000. And from here we got the solutions, which are x equal 1,000, y equal 1,000, and z equal 1,000. So by using elementary transformation to reduce the augmented matrix to echelon form, we get a new system of equations with the same solutions as the original, and we call this as Gaussian elimination. Now, the coefficient matrix of a linear is having the coefficients of the variables only without the constant. So in a matrix which we are presenting the values of coefficient without the constant. So here we have this coefficient matrix. Why we introduce coefficient matrix? To just compare about something really important, which is rank. So a rank of a matrix is a number of a non-zero row left after their matrix has been reduced to echelon form. Why we need to introduce this? Because the rank of augmented matrix and the rank of coefficient matrix should be equal to find a solution. Otherwise, we have to identify something else. So in case the augmented matrix rank is here, after eliminating the matrix to echelon form, we got the last row as zeros, and there is a number of a constant in here. In this situation, the linear equation does not have a solution, no matter what values we substitute for the unknowns. Yeah. So the rank of augmented matrix in this case is greater than the rank of coefficient matrix. So this is the first situation we have. If the rank of the augmented matrix is greater than the rank of coefficient matrix, where I have a constant, so c does not equal to 0, then the linear equation does not have a solution. All right, how about if again the augmented matrix rank is greater than the coefficient, but I got 0 in here, c equals 0, then this linear equation has infinitely many solutions. Why do you think? Because I can just apply whatever to the let's say the variables, and I will keep getting the results. That's why if c equals 0, I can have infinitely many solutions. So to summarize the rank concept, a linear equation can have a unique solution if the rank of the augmented matrix equals the rank of coefficient matrix. It will have infinitely solutions or many solutions if the rank of augmented matrix is greater than the rank of coefficient matrix and c is equals 0. And the linear equation have no solution if the rank of augmented matrix is greater than rank of coefficient matrix and c does not equal to 0. And here we reach the end of part 3 and the end of lecture 4. So never give up, because great things takes time. Thank you guys for listening to lecture 4. In case you have any queries, do not hesitate to contact me through my email, which is mentioned on the footer of the slides. Wish you all the best and stay safe.